What makes calculating higher-order transfer functions so difficult? Imagine trying to solve a puzzle where each piece is a complex mathematical expression. That's what calculating higher-order transfer functions feels like. These functions are used to understand how signals move through systems in electrical engineering. They show the relationship between input and output signals in the frequency domain, expressed as ratios of polynomials involving the complex variable s. When the system has many energy storage elements like inductors and capacitors, the order of the transfer function increases. This makes the polynomials in the transfer function become very high degree, which is where the trouble begins. Starting with the basics, a transfer function is derived by applying the Laplace transform to the differential equations that describe the system. This transforms time-based derivatives into algebraic expressions involving S4 simple systems with one or two energy storage components. The resulting polynomials are low degree. Finding the poles and zeros, which are the roots of the denominator and numerator respectively, is straightforward. But as the system gets more complex, with more inductors and capacitors, the characteristic equations become high-degree polynomials. These are much harder to work with. One big challenge is algebraic complexity. High-degree polynomials have many terms, making symbolic manipulation difficult. Factoring these polynomials to find the roots is often not possible with simple formulas. Engineers usually need to use numerical methods to approximate the roots, which can be time-consuming and sometimes less accurate. Another difficulty comes from multiple poles and zeros. When many are present, their interactions can create complicated behaviors. These include resonances, oscillations, or slow responses that are tricky to predict. Analyzing how these poles and zeros influence system stability and response becomes more complicated as their number grows. Stability analysis is also more involved. To check if a system is stable, engineers look at where the poles are in the complex plane. For higher-order systems, this process is more complex because the root locus or Routh-Hurwitz criteria involve more steps and calculations. Graphical methods become less clear, and small changes in parameters can cause big shifts in pole locations. Computational resources are another concern. Solving for roots or simulating responses in high-order systems requires more powerful computers. Numerical methods can be sensitive to small errors, leading to inaccuracies in the results. This makes it harder to rely solely on analytical solutions. Because of these challenges, engineers often use approximation techniques. For example, they might simplify a high-order transfer function into a first-order plus dead-time model. This makes analysis and controller design easier but can lose some detail about the real system. In real-world electrical engineering, such as designing filters or amplifiers, higher-order transfer functions naturally appear. Managing their complexity involves using software tools, approximation methods, and frequency domain analysis techniques like Bode plots. These tools help engineers understand system behavior without getting lost in complicated equations. In summary, calculating higher-order transfer functions is difficult because the algebra becomes very complicated, multiple poles and zeros interact in complex ways, stability analysis is more involved, and the computational effort increases significantly. These factors make exact solutions impractical, so engineers relying on approximations and numerical methods to work with these systems effectively.